Recording is rolling. It is Friday, October 25th. You guys have a red string on your desk. We're about to do an ellipse activity. So be ready for that. Yeah, you guys get your notebooks out. So this can go in your notes also. Talk about universal gravitation today. Guys, after I talk about universal gravitation today, going into the weekend, I think at that point, by the end of today, you'll have enough information. You'll be able to solve any puzzle from last few weeks. So guys, what's due by the time you guys come into school Monday morning? AP Classroom Unit 2? Hearing that? Yeah, progress check. Yeah, progress check. So have that done. Yeah. Most of those you could have done already. Some of you guys have already started those, solved a bunch of those, but by the end of today, you should be able to solve the rest of them. Right? The ones that deal with gravitation. Here, I'll throw a due date for Chapter 7 puzzles. Chapter 7 puzzles. Let's call those due 1 week from now, Friday. This is a paper I gave you guys a long time back. Looks like this, Chapter 7. Okay. So we've been slowly covering the topics, the materials, but there's still a few that have to cover today, like how to set up and solve them. Okay. I'd like to fit in at least a day next week to give you guys some time in class to work on, but not 100% guaranteed because there's a lot of things I gotta fit in, and so we'll see. Today's picture retake day. If you didn't get a picture, you need to retake it, then find a good time sometime today to go down there. Okay. All right, and all right, hurricane makeup. So here's the news I'm getting on that is the makeup class time. There's going to be no early release days in November, so Fridays are going to be regular length. Oh yeah. No, if just go ahead. It's in the gym. Yeah. So if you need to go to the gym, just go ahead. Okay. All right. So you guys got all that? All that. All right. Oh, also next week is going to be a no to drugs week, red ribbon spirit week. So here's what we got going. I'll just tape this up in my room. We got Monday, wear white, wear pink, wear blue, wear purple. Tuesday, wear neon. Wednesday, wear a jersey. Thursday, scare away drugs with Halloween outfit. No mask. Friday, say no drugs, wear red. Follow dress code. You go there. All right. Let me switch my screen over to this screen. Let's do this one. All right. I want to do a little follow-up from yesterday before we hit the ellipse activity. So you guys remember I showed you this yesterday? And Alec asked a really good question. He was saying, is the tension in this slinky the same all the way down or not? And I didn't know the answer right away, but then I should have because I thought about like 1 minute. It's, oh, okay, obviously. Right. Guys, a lot of times if you see some kind of spring, you'll see in the setup, they'll say, assume that the spring is massless. They'll say something like that. Right. Now, that's probably not exactly true, but maybe that kind of helps simplify the problem for some reasons. Right. Guys, if it was a massless spring, would the tension be the same everywhere? Yeah, that would be true. Right. But if it has significant mass, which I think it would in this case, because the mass would have a weight, right? And that would enter into this also. Right? Guys, if it has a weight, like a mass, isn't that more like a vertical chain of links? Right? And this is something we talked about a few weeks ago, isn't it? Right? You guys remember like the vertical chain gang or barrel of monkeys, like that? Okay. In which case, where is the tension greater, near the top or the bottom? Yeah, definitely near the top. Okay, so that's probably more realistic. Okay, so wanted to go back and hit that. All right, let me bring this back over here then. All right, so you guys have a ribbon on, or a string on your desk. Or you guys got a string. You guys got a string? Okay, so go ahead, tie this into a loop. Tie it into a loop. Okay. If you happen to have 3 pencils, that would be helpful at this point. But if not, then well, just do your best on this. This is just an activity for your notes. I'm gonna have you guys do this in your notebook. You're about to write something down with this loop. Right. So you guys got a knot tie, made a loop. Right. So make a loop like you're tying your shoes, and then just do that again, and it should make a nice strong knot right there. Okay. And so you got to loop a string. You guys got to loop a string. Yeah. All right. Next thing we're gonna do is right now. I do have 3 pens myself. If you can have 3 pens or pencils, or figure out how to makeshift something like this, I'm gonna put down 2 pens right here. Actually, let me open these up. Click. All right, to get some points on the board. Right there, right there. All right, there you go. That's better. Okay. And then with your third pen or pencil, go out like this. Right, make it, ooh, what shape is that? Triangle. It is a triangle. All right, you guys are on. All right, now with this third point, right, the first two are locked in place. With this third point, go all the way around. Right. Yeah, it is kind of like a compass, isn't it? Except a compass would have one point, and here I got two. Actually, these two pins that are fixed in place, those are marking what are these 2 points called that are fixed in place? Starts with an F. Focal points. Focal point, or yeah, the plural is foci, isn't it? So this is a focal point. This is a focal point. All right, you guys got that? Okay. And the shape you just drew is called a what? Ellipse. Yeah, here, I'll write that down. Ellipse. All right, ellipse. All right. Okay, here's it. Okay. And here, do some more stuff on ellipse. Did you guys study ellipses in maybe algebra 2, maybe? Or no, maybe I don't know. I went to school a long time ago. Who knows what they're doing? Okay. So I'm going to mark a couple of axes. Do you guys see that this axis would this be the longest axis you can make on this ellipse? Yeah, this is a long axis. Let me measure exactly what. So mine happens to be, it looks like 18 centimeters long. Mine's 18 centimeters, my long axis. And my short axis, let's see, what is this? Ooh, this is like 17 and a half centimeters. Okay, so it's a little bit less. It's subtly less, but it's a little bit less. Guess that? Right. Now, guys, what if your two focal points were actually at the same point? What if they were right on top of each other and you did the same thing? You would have created a what? A circle. Talk about circle versus ellipse. Okay. So circle. Guys, what is the area of a circle equal to? Area of a circle. Pi r squared. Pi times r squared. I know radius is some linear unit. If I square that, I get a square unit, like an area, multiplied by pi. Right. Oh, how about for an ellipse here? I'm going to call this long arm B. I'm going to call this short arm A. Is that okay? This can be A, and this can be B. Right. And if I do this with this, right? You guys see, I just dashed off. What shape is this right here? It has width B and height A. The rectangle, right? Rectangle. Is that rectangle? Okay. Guys, that area of the rectangle is A times B, isn't it? A times B, area of the rectangle. Okay. Guess what? I bet you guys can figure this out. What is the area of the ellipse in terms of the area of that rectangle? Here you guys a hint. If you squash this a little bit, it would be a circle, right? And this would be R, and this would be R. And no, it doesn't. This would be a square. What the area of the square would be R squared. How do you go from R to area of a circle? Pi r squared. Hey, and r squared would be, this would be a squared. And then times 3.14, and now you have the circle. Okay, well, with an ellipse, I have A and B. So what's the area of the ellipse? Aha, it's pi AB. You figured it out. It's pi AB, isn't it? So here, if you cash in this rectangle right here, multiply it by 3.14, that's equal to the area of the whole ellipse. That's it. Right. Here, got another question for you guys. What's the circumference of a circle equal to? 2 pi r. All right. What's the perimeter around an ellipse equal to?
2AB.
Turns out nobody knows. Nobody's ever been able to figure this out. Even the most brilliant mathematicians in all of history have never been able to figure this out. So, a big question there. Because it turns out, I guess it's a really tricky question to answer. But here, maybe you'll figure it out. All right. So let's go back. Oh, whoops. I shouldn't have done that. Hold on. Sorry, I'm still trying to get used to my new system here. All right, I hit the wrong button. All right. Okay, I think I just have to wait for that to go off. Is this gonna come up here? All right, hold on. All right, here's what I'm going for. All right, so guys, yesterday just started talking about gravitation, ran out of time, so we're gonna kind of pick up from there. So let's say it's guys, it's 2,000 years ago. Oh, and you're looking at the night sky, trying to figure out how everything works, and you make a model. Now, this is an animation of that. Do you guys see what's that symbol right there with the circle with a cross in it? That's a symbol for what planet?
The Earth.
Earth. Ah, that is the Earth. Oh. What do you think that big old bright point is? The sun. Go with the sun, right? Right. And then these two guys are Mercury and Venus. I think this one's Venus, looks like, right, and this one's Mercury. Pretty sure. Right. Now, from the point of view of Earth, from the frame of reference of Earth up in the night sky, this is what it looks like is going on. Right, it looks like the sun's going around the Earth. right? And it's 2,000 years ago. Like, how would you tell the difference? I mean, kind of hard, right? Right? And maybe you can eventually figure out, well, maybe the Mercury and Venus are going around the sun, or relative to Earth, are going some kind of loop-de-loop fashion. But maybe you can figure that out, right? But guys, what's this one right here? Hmm, Mars. That's Mars, right? It's Mars, right? Now, from the point of view of Earth, here's what it looks like Mars is doing. Okay, it's going around the Earth. It's going counterclockwise, it looks like. And then, oh, whoa, what is that? That looks that loop-de-loo in the sky where it like goes backwards. It's called a retrograde. It looks like it's going clockwise just a little bit, and then it spirals back and goes counterclockwise and on its way again. Right? Now, this is called a Ptolemaic model after Greek guy Ptolemy. Right? So he had this Earth-centered model, and everything's going around the Earth. That's what they thought 2,000 years ago. Right? Except if you make really precise measurements, yeah, you can see things like this. Like Mars has this retrograde. How do you explain that? Well, they'll just build that into the model. Okay, I guess it spirals every so often, something like that. And okay, so that could fix it, right? Right. But a long time ago, did I tell you guys who was the scientist who came up with the sun-centered model? Copernicus. Yeah, all right, that's it. Yeah, Copernicus. Right. So this is called heliocentric. Helio sun, centric center, sun center, heliocentric. He said, hey, if you put the sun at the center, you don't have to worry about the loop-de-loos at all. In fact, what math equation would even explain that? This is a lot simpler. Everything's just going around the sun, right? So that could actually explain that motion there, right? Right. So that was well, controversial at the time, but hopefully that's what you learned in school because you guys know the sun is at the center, right? Okay. Actually, strictly speaking, what's at the center is the center mass of the whole solar system. It's called the Berry point of the whole solar system. So if you took like the average mass value of like everything, or yeah. It is, yeah. So basically, it's just because the sun is like 99 point something percent of the mass of the entire solar system, which is like almost all of it. Yeah, so you could basically call the sun the center. Yeah, right. But like let's say Pluto has a moon. Or actually, Pluto has a couple moons, but I think the big one's called Charon. And Charon and its Pluto actually orbit about a point that's just outside Pluto. So the Berry center between those two is not actually inside Pluto. Actually, between the Earth and our own moon, the Berry center is not the center of the Earth, but it's kind of closer to the surface. It's still inside the Earth. So the moon and the Earth kind of orbit a point that's still inside the Earth, but it's kind of closer to the center or surface in it. All right, so we got that. All right, so did a couple of demos there. See what I want to do for the guys. We got okay. So I think I was just talking about this in the bell was ringing yesterday, right? So Copernicus is coming guy says planets move around the sun, and then Kepler takes this extremely precise astronomical data that he was able to get hold of. It says actually more specifically it's ellipses. That's why I had you guys draw an ellipse. Guys, that ellipse you guys just drew with that string, that is actually the shape that planets make around the sun. This is what they do. This ellipse. And the sun is at one of those focal points. So you guys had those two dots for the focal points. One of those could be the position of the sun. Right? Second law, equal areas at equle times. So it's a little slower at the aphelion, a little faster around the perihelion. Okay. Right. And all right. Then this third law, he says, if you look at the time period to go around the sun. So for Earth, guys, what would time period be for Earth around the sun? 365 days. Right? And the radial, now this R is not constant because it's a ellipse, but it's barely an ellipse. It's pretty close to a circle for planets, right? So you can say like an average value. So for Earth to the sun, I think it's about 150 million kilometers, something like that, right? So if you keep that, there's a direct proportion for all planets in our solar system, as long as they're orbiting the same mass, which is the sun in this case, right? This ratio, if you take t squared over r cubed, that's the same ratio for every single planet in our solar system. That's as much as Kepler was able to figure out. And we're about to bring in Newtonian mechanics because Newton comes after all this, right? And we can make an exact equation. The exact equation ends up looking like this. So we're working our way towards that. All right, this one right here. So Newton was the first guy in recorded history to make the connection that an apple falling from a tree and the moon orbiting the Earth are actually part of the exact same phenomenon. People didn't realize that for thousands of years. That, oh, well, there must be terrestrial laws where things want to fall straight down the straight lines, and there must be celestial laws where things want to like orbit the Earth, I guess, or something. But Newton says, hold on a minute. I think it's all the same thing. I think that the moon is actually attracted to the Earth, but that it has such a great tangential velocity to the side that's actually falling around the Earth. Right? And I can show that with some math that we're going to do. Like, I'll have you guys derive orbital speed later. You guys all got your notes out for sure, right? You guys got your notes out, right? So let's break down this formula and look at some details. And later on, I'll have you guys derive orbital speed, which yeah, Newton made the connection with. Okay.
Why is gravity 6.67?
Ah, yeah. What's this big G right here? Okay, yeah. Hang tight. That's a good question. So yeah, I'll answer that in a few minutes here. All right. So Newton says the gravitational force between, let's say, the Earth and the Moon. Here, you guys remind me. Because which force is greater, the Earth pulling the Moon or the Moon pulling the Earth? They're the same. That's the same, right? Because Newton's third law of motion. They're the same force. The magnitude of that force, which is the same both ways, is well, it's proportional to each mass. So big M could be whatever's being orbited, in this case the Earth. Little m could be whatever's orbiting, in this case the Moon. Okay, so multiply those together and divide by the distance between them squared. And I'm about to show you guys why it's 1 over the distance squared. Okay, guys, what distance am I talking about? Guys, focus here. Am I talking about the surface to surface distance or the center to center distance? Center to center. You guys do say that, right? Right. So when you guys draw this yourselves, you get that. It's like from the center mass to the center mass. That's what that is, right? So that's the distance. So 1 of the distance squared. Now that's all proportional so far, like m over r squared. Now, if you want to make that an exact equation, you need to throw in some constant to tie it all together, and that's what capital G is. It's called the universal gravity constant, and I put the value down here. But yeah, I'm going to talk a little bit more about that too. Okay. So 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. If you plug that in, all the units work out because mass is in kilograms. This mass is also in kilograms. This radial distance arc, that could be in meters. Okay? I need this force to be in newtons. Okay, so even if I didn't tell you this unit, I bet you could figure it out just by what units would make that consistent. Right? You guys good? Okay. Guys, 10 to the negative 11. Is that an extremely large or an extremely small number? Small. That's like 0.0000, string of zeros before I hit 667. Right? Here's that.
Isn't M?
Well, capital M is the mass of the Earth. Lowercase m is the mass of the Moon. So this is like, I think this is like 10 to the 24 kilograms. I think the Moon's like, I have to look it up. It's probably like 10 to the 22 or 10 to the 23 kilograms, something like that. Yeah.
Substituting, can you do it with another planet and it's like Jupiter and
Mhm. Yeah. You could do this with other things too. Guys, you could put any masses here. You could put the mass of the sun and the mass of the Earth because the Earth could be orbiting the sun. You could put the mass of Jupiter and the mass of Io. Or, you could put anything that's gravitationally attracted. Right? Actually, you could even put the mass of the Earth and your mass. Guys, what's the distance between you and the Earth using this model? The radius of the Earth, isn't it? Right, guys. When I say the distance between you and the Earth, we're treating the Earth as the center mass of the Earth. That's at the center, and you are all of us are one Earth radius, or one Earth radius away from the center of the Earth. Right. So you could do this, guys. If you plug in the mass of the Earth here and your mass here, and the radius of the Earth here, maybe I'm like that capital R for like a fixed radius, and I put in capital G here, which is this number, and you run the numbers, that represents what force? Your weight. Yeah, your weight, right? Is that what this? Right? And I suppose I go to the edge of a cliff and drop something in free fall. Hey, could you modify this to get the gravity free fall at Earth? Right? How could you modify this a little bit to get not a weight force, but an acceleration due to gravity? You just eliminate one of these variables. Which one do you knock off? Yeah, the little m, right? Isn't it true? Go to the isn't this the Galileo experiment? Leaning Tower of Pisa. He drops light stuff, heavy stuff. It all falls at the same rate, right? And you guys did some experiments like that too. So capital G times capital M over the radius of the planet squared. If I just look at that bit right there, that could represent the gravity field of a planet. Right? You guys that too? Right? But I still haven't told you guys why it's over r squared. You guys ready to see why it's over r squared? Okay, because 1 over r squared is something you see all over the place in physics. You see it for gravity there. You see it for electrostatic force, like electricity, like charges. You see it for, let's look at a light example, because I think this one's pretty intuitive. It's pretty good. All right. So let's say you light a candle. All right, you guys get candle flame, light a candle. Let's say you're standing 1 meter away from the candle. You see that? Right. And then you say, wow, that's pretty bright. And I see the light cone right here. So you step away to 2 meters away. You see you doubled your distance away from the candle flame. Right? And guys, that light cone going from 1 meter to 2 meters away now covers how many times the area on the back wall? So 4 times the area. Therefore, your pupil, which is the fixed size, captures what fraction of the light? 1/4. Now you back up to 3 meters away. So now you're 3 times your original distance. the back wall, that light cone covers how much of the back wall? 9 times. Therefore, your fixed pupil size captures how much of the light? 1/9, right? Yeah, right? You guys get like 1/9, right? Okay, so what if you're like a mile away? Maybe you barely see the candle flame at all because it's 1 over. Okay, so it's 1 over the distance squared, right? Guys, this is a consequence of living in a universe with 3 spatial dimensions. You got up, down, right, left, back, forth, right? Yeah. So as you back away from it, say along the x-axis, the y and z axes, it's like a surface area. Okay, so okay, all right. The other thing I got to mention, so we're back to this. I explained 1 over distance squared. The other thing we had is, where do you get this capital G from? Okay, so Newton nailed down the force is proportional to each mass and divided by the distance squared. Actually, how he was able to figure that out is he did the math to show that this would be the only force relationship that could explain elliptical paths around the sun, right? So go back to Kepler, because people don't know, like why ellipses? We do see factually it's ellipses. We have these Kepler's laws of motion, and that's well established. But why? Newton said, okay, because it's 1 over the distance squared is proportional to the force. We got that, right? But if you want to make an exact equation, you still need to figure out what constant is going to tie this together. Now you guys see what that constant is. It's this G equals 6.67 number, 10 to the negative 11. Okay? All right, so where'd that come from? That comes from a guy named Von Jolly in 1880 did this experiment. Said, I'm going to start with this balance. All right, so got a balance here on a fulcrum. See that mass and that mass, and it's all balanced out, so it's all good to go. Then I'm going to roll a big old 6 tons of lead underneath one of these masses. And I know the center to center distance. And I also know Newton's universal law of gravitation. You guys, do you think there'd be a tiny, tiny gravity force between these 2 pretty heavy masses? Yeah, right. You think that balance goes just a little bit out of whack? Right? Maybe leans a little bit counterclockwise. Right? Then what he does is he takes another mass here. I put this red apple here to restore that balance. Right? So this has some weight, and I've labeled that a force because weight's a kind of force. Right? And then he tries this for all different combinations of masses and distances, and he always gets the same ratio. He takes this force, divides by this m and this m and this distance squared because he knows Newton's universal law of gravitation, and he always comes up with the same constant, and it is the universal gravity constant. Okay, so that was the original way he figured out 1880. Got that? All right, guys, good so far. Good so far. All right. Okay. Now this one kind of notes here. I'm gonna go with this with you guys. You guys need to know this. You could get asked questions about this. I really made this for AP too. Right? Suppose there's some planet X out there. I'll walk through this kind of fast, but maybe you want to slow down and look at this later. Maybe watch this video later. Right? And let's say the planet X has a radius 3 times the size of Earth. So it's like 3 times the radius, 3 times the diameter. You guys got that? Okay. Now, guys, if you knew nothing else, let's put a pause for a moment. If this planet had the same density as Earth, then how many times more massive should it be? 3 by 3 by 3. 27 times as massive. You guys remember that scaling poster from a long time ago? Right? If you scale it different, properties scale it differently. Right? It'd be 27 times the volume. And mass occupies volume, so it should also be 27 times the mass. What if I don't tell you that? What if I say this planet, no, it's not that. We'll say it's only 7 times the mass of Earth. Now, guys, if it's only 7 times the mass of Earth, and not 27, which is probably more realistic, right? Is this a very dense planet or not so dense planet? Not so dense, right? It's only like 7 compared to 27. That's what or 7 compared to, yeah, 3 times 3. Sorry, that's about a quarter of the density that it really should have. I think it's a giant puff planet. Maybe I made out of styrofoam or something. Giant puff planet, right? So here, guys, isn't density mass compared to volume? And that's what's in red here. So here's the mass of Earth compared to the volume of Earth. Guys, is volume of a sphere 4/3 pi r cubed? That's volume of a sphere. You guys, that's on a poster from a long time ago. 4/3 pi r cubed is the volume of a sphere. Right? Now, even if you didn't know the 4/3 pi bit, that's okay because this ratio ends up canceling that bit out. The important part is the radius cubed part, that the volume is proportional to the radius cubed. As long as you know that, you'll still get this correct. Okay, even if you don't know the 4/3 pi to turn it into a proper sphere. Okay, that's good. All right, now, so that's down here in the denominator. I got the density of Earth. This is Greek letter rho for density equals. Okay, so here's for Earth. Now this planet is scaled up by some factor. Notice I haven't given you any hard numbers. I didn't give you the mass of the Earth or anything like that. We're just looking at ratios. Right? So 7 times the mass of Earth. and 3 times the radius of Earth. Guys, that factor of 3 gets cubed. Don't forget that. So if you take this ratio, a bunch of stuff cancels, and you get, that ratio right there. Notice that's less than 1, right? So yeah, so the density of this planet X is less than that of Earth. Yes, yeah. Right. Right. So be able to do that. I know we went over that kind of fast, but I'll let you. All right. How about the gravity field on this planet X? I mean, it's a larger planet. It's more massive. It's more massive. Should that make you heavier? Yes, but larger radius makes you further from the center. Should that make you lighter? So do you guys see that there's 2 competing effects? Right. More massive should make you heavier. Larger radius in isolation puts you further away. Should make you lighter. Okay. So what's the aggregate effect here? Right. So got gravity field. You remember gravity field? We just talked about this as gm over r squared, where this m is the mass of the planet. Right, so here it is for Earth down here. If you run the numbers, you'll get like 9.8 meters per second squared. Okay, so you guys know that. Right? Now this planet, I'm just scaling by some factor. 7 times the mass, 3 times the radius. That factor of 3 gets squared. Right? Yeah, a bunch of stuff cancels, and it looks like 7/9 the gravity field of the Earth. So actually, you'd be what? A little bit light or a little bit heavy? A little bit light, because 7/9 is a little bit less than 1. Okay. So you'd be a little bit light on this planet. You could jump a little bit higher. Okay. Guess that? All right. So I'd like to spend more time on that, but got so much time, so I'm gonna move on here. Okay, this one. Here's where we're gonna jump away for a bit. Because I want you guys to derive this one from scratch. Right? Because this is where, and guys, we're gonna do this. This is whoops. And then hold on, how does this work? I forgot how this works. Hold on. Wait, here's where, okay, I think we're back. All right, we're back here. All right. All right, so title this orbital speed. I'm probably going to have you guys derive this a few times throughout the year. I remember last year for review, I had students derive this a bunch. Right. Orbital speed. Okay, so this could be any satellite orbiting any planet. This could be the moon orbiting the Earth. Guys, is the moon just a natural satellite of Earth? Yeah,
Yes.
it is, right? Yeah. Right. So let's have the Earth. Actually, I'll just show how about a regular satellite? Okay. So here it could be the radius of the Earth. Okay. Now, guys, suppose you see the International Space Station go across. You guys ever seen a satellite go across the sky? Maybe. Right. Watch the sky long enough, especially if you go out west where there's no light pollution. You see one about every minute. Right. Because those satellites, how far up are they? Yeah, just above the atmosphere. Yeah, it's only about 400 kilometers, 400 kilometers, which in proportion to the radius of the Earth, the radius of the Earth is like, I think it's like 6 times 10 to the 6 meters, I think, something like, all right, like millions of meters. Right. Proportionally, it's not that far up. So if you want to figure out what is the orbital speed around a planet, it's like just above the atmosphere. This distance from the center of the Earth is not that different from the radius of the planet itself. So we're going to just kind of approximate and say it's about the same. Or if the atmosphere of the Earth is really thin. I think I've heard like if the Earth was the size of a basketball, you take plastic wrap and just wrap that around the basketball. That'd be the same proportion as like how thick is the atmosphere on Earth, right? It's pretty thin in the big scheme of things. Right. So we're going to say this is approximately the radius of the Earth up. Right. And it's got some speed. I'll call that v. Right, to go around. Right. Now, this is what Newton is thinking for the moon. We could do this for the moon. Well, the moon's way out here, but it's the same idea. Right. So, guys, I should have drawn this bigger. That's okay. Guys, draw a free body diagram on that satellite right there. Free body diagram. What's one force acting on the satellite? It's gravitational force, it's weight. Maybe I'll call it F sub G. F sub G. You could do mg, but I want to be a little bit careful because you guys think the gravity field is getting weaker the further away you get? Yeah. So let me say more generally F sub G, force due to gravity. Okay. Is there any other force on that satellite? Nope. That's it. That's the only force. Guys, if that's the only force, that would be the net force, wouldn't it? Right? Is that satellite in equilibrium as it's going around? No. You might say dynamic equilibrium if the radius is not changing, but not true static equilibrium. If AP asks you, they always care about inertial frame of reference, so probably avoid that word at all, equilibrium. Don't even say that, right? Right, so I think that gravitational force is acting as the what kind of force to keep it in a circular path? Centripetal. Guys, do this. Say centripetal force equals gravitational force. Okay, that's hold on. Let me see. I think I got the wrong screen up there. Should it be? Is that better? Okay. What's going on? Is that okay? I don't know. That's working. Okay, so you guys good? Okay, so centripetal force is providing the gravitational force, right? Okay, okay. All right, this is the first domino that's going to kick off a chain that's going to lead you to solving for this orbital speed, right? Well, orbital speed, the variable speed has to show up somewhere. So, guys, what's the expression for centripetal force? Exactly, mv squared over r. Okay, all right. Guys, which m does this refer to? The mass of the satellite. Satellite. The satellite might have mass little m. The mass of the Earth I'm going to call mass big M. Okay. Right, all right. Okay. And yeah, this is the mass of the satellite. Okay. Whatever's like orbiting. Centripetal force. Okay. Now I just showed you guys, maybe remember from a minute ago or wrote it in your notes. What did Newton say was the formula for gravitational force? Aha, GMM over R squared. Right? Right. Let's get that. Okay. Now this radius is really the radius to curvature. If it was the moon, I could do little r here and maybe little r also here. But it is the same r. Okay, it is the same r. Right. And if I say this is orbiting pretty close to the planet, I say, well, that r is pretty close to the radius of the planet. I'll approximate a little bit. Right. Right. Oh, guys, what are we solving for? Yeah, tangential velocity, the speed right here. Can you guys do that? Go ahead. Go ahead. Do a little algebra. Solve for that v. See if you guys get the right answer. If you can get it right now, that's a good sign. Yeah, so Alex got it. All right. Yeah. Ben about to be getting a bunch of winners here. Yeah, okay, yeah. I think you guys are getting this. You guys are getting this. So you're just doing a little algebra. You're just solving for that V. I would normally give you guys an extra minute, but got a Friday schedule, so let's move it on here. What canceled?
Radius.
Yeah, part of the radius. And the mass of the satellite. So, and then you just take the square root. Actually, that's the only algebra step left. Take the square root. So, and this is orbital speed equals, right? It is the square root. I got universal gravity constant. I got the mass of whatever's orbited, in this case, the Earth, divided by the radius that it's orbiting, radius of curvature. That's it. There's your orbital speed right there. That's a good one to know. Also, that entire derivation process, the AP could ask you that as a free response question. Yeah.
Does that mean that no matter what object orbits it, it goes at the same speed?
Exactly. Yeah. So, here, look, ask you guys an application question. Suppose you got International Space Station. It's going some speed. By the way, if you run the numbers for this, it ends up to be about 8,000 meters per second, pretty close. Right? And now let's import a bunch of space groceries. They're getting hungry up here. So we bring in a bunch of space supplies, a bunch of space groceries. Now it's a lot more massive. Do you have to speed this up, slow this down, or keep the same speed to stay in orbit? Same speed. Yeah, exactly, because mass of the satellite canceled out. If you have a small satellite, a large satellite along the same radial path, yeah, same speed, right? Whatever that is. It does not depend on the mass of the satellite. All right. All right. So let's go back here. Oops. I got to switch my screen on the Zoom. All right. Okay. Now this needs to come over here. Share my screen. Okay. I think this is going to work. All right. Okay. There it is. That's what you guys just did, right? You guys just did that? All right. All right. I also have here, guys, escape speed. Now, this involves future content we haven't talked about. So depending on the order you teach this class, there's different ways you can teach this class. We haven't talked about energy yet, but using conservation of energy, you can solve, you need to know this anyway. I'll tell you guys, right? How fast do you have to send a rocket so you could cut off the engines and it's still going fast enough where it could escape the planet's gravity and fly away? If I toggle back and forth, do you guys see these two formulas, orbital speed, escape speed, look pretty similar? Just flip a 200 to the square root. Guys, square root 2, is that like 1.414? Right, so if you know orbital speed, multiply by 1.414, that's how fast you have to go to escape speed, right? If you read your chapter 7 questions, textbook questions, there's a question that says, prove that escape speed is proportional to the radius of the planet. That's one of your questions. For that matter, you could have swapped out and said orbital speed. Like, how fast do you have to go to orbit Mars? How fast to orbit Earth? How fast to orbit Jupiter? Turns out that's also true because the same proportions apply, right? But for your textbook puzzle, just start with this so you're allowed to know this. So just take this as a given, right? And you have to prove a proportion. And guys, when you're proving a proportion, let me scroll back a few slides here. It's the same thought process as each of these. You guys see these? but I did this one for density and this one for gravity field. But do you think you could do the same type process for like orbital speed or escape speed if you wanted to? Right? That's one of your textbook questions. It's a good challenge question. See if you guys can do that. Here's them all on one nice page. Convenient. So here's the gravity field of a planet, just GM over r squared. M is the mass of the planet. Here's orbital speed. Here's escape speed. Boom, boom, boom. They're all right there. Okay? I'm all right there. All right. All right. There's some more stuff I want to do, but I know bell's going to ring in like 30 seconds here. Okay. Yeah, I think I'll have to hang that recording right there. Guys, on Monday we'll do AP Classroom, of course. Right. If I have time to fit these slides at some point, I do want to talk about these other ones, but right now I'm just gonna have to leave that right there.